Okay, getting started here. I didn't see Amanda. Is Amanda here? And I didn't see Jaron. And I didn't see James. And lest you wonder, yes, I know my team got horribly beaten yesterday. They looked pathetic in the process. But you're not a fan if you can't stand up for your team when they're beaten down. So, I wear my jersey. We are reviewing today. That's why there was no no reading quiz before class. Likewise, there'll be no homework due on Wednesday because we're not doing any new material today. But there will be an exam during the lab period, mañana, tomorrow. Ashita. Yeah.
Will there always be homework before the test on the Friday?
There should be homework on every day except for the day following the test, because we're reviewing the day before the test.
So the material that we learn on Friday is not necessarily going to be on the test?
Oh, definitely not.
So we are going to have homework, right?
Yeah. But it's due on Monday. It's not due on Tuesday. So the chapters that we are going to be covering on the test are chapters 1, 2, and 3. The titles here: Introduction, Kinematics, and Two-Dimensional Kinematics. So let's quickly go over some things. One of the important things in chapter 1 was quantities and units. So we have, I had this open. I thought, try it again. Today's September 14, right? Is it? Okay. All right, that's right. So, a clicker question dealing with these units and quantities. What is the base unit for time? Remember, it's channel 33. Yeah.
In the spirit of not memorizing physics,
Yes.
to know the wavelength definition of a second, that kind of like memorize those numbers.
No.
Or just conceptually, and maybe we measure it in vacuum.
No, you don't need to know that it's, well, maybe I misunderstood. You should have an idea that there is a standard that is the measurement of, X number of wavelengths of a specific transition. You don't have to know what the number of wavelengths is, certainly, or what the transition is, or even what the element is. Yes. Okay, we had 22 answers, and they all agreed. The second is the standard unit of time. And obviously, since all 22 of the people who answered got it right, which is everybody here, since there are 2 people missing, that was a trivial one that you know, and hopefully these next 2 are easily the same. What is the SI base unit for distance? One person that answered before hasn't answered yet. Go on. Okay. 21 people said the meter. And that is also correct. Now for our third of these, what is the SI unit for mass? And this one here is not perfectly as simple as the others, but it's not difficult. Okay, so we have 15 that said the kilogram and 7 that said the gram. I was right, not quite as simple as the other. The majority is still correct. Why is it not quite as simple? Because you tend to think that the prefix should be part of your base unit, but it is. The kilogram is the base unit for mass rather than the gram. You know, honestly, I don't know what a carat is. I know they use them like in gyms. The slug, has anybody, you know, in your reading or your reading quizzes, learned about the slug? Well, what is the unit of force in physics? The SI unit of force? Newton. I say in physics. Yeah, that was bad. This here is the SI unit for force. And it's equal to 1 Newton is equal to 1 kilogram times a meter per second squared. That's a derived unit. Our test won't have forces on it, but you could have still the derived unit for force. That was part of chapter 1. But we won't have any force problems. The slug is the mass unit in the imperial system, such that the unit of force in the imperial system, 1 libra, or 1 pound, LB stands for libra, is equal to 1 slug times a foot per second squared. And so the slug is to the pound as the kilogram is to the Newton. They're the base units for mass. But who's ever heard of slugs? Right? We've heard of pounds. We always measure our weight in pounds, but we never measure our masses in slugs. And I would just love to go to one of those places where, I mean, they're not really measuring your mass, right? They're measuring your weight and then calculating your mass from it. I would just love for it to say, yes, you have a mass of 73.5 slugs. And, you know, let people sit down and think about that. I'm probably the only one in the world, but it's okay. Okay, enough for our base units. Next we had ideas of accuracy, precision, and significant figures. Now I'm going to have a couple clicker questions dealing with the significant figures, but let's start with accuracy and precision. How do we differentiate those two terms? Lindsay.
Accuracy is when you get it as close to the value it's supposed to be, and precision is when you get it all in the same spot.
Okay, that's exactly right. So accuracy and precision, close to correct is accurate. You know, so that we always use examples like shooting arrows at a target. But in measurements, you might be measuring the spacing between, you know, studs in your wall or something. And if they are accurate, they're all close to, you know, the 24-inch centers or whatever you're trying to do. They're not going to be necessarily all exactly 24 because, you know what, they never are exactly 24. But they should be pretty close to that. You could have, you know, somebody who's supposedly building a wall with 24-inch centers and they decide to save money and put them all 26 inches apart. It would still be precise if they're all 26 inches apart, but it's not accurate. It's not the right measurement. Now, that would be a construction thing, but, you know, idea. Okay, so that's the difference in those. Then significant figures. Why do we use significant figures? Oh, boy. That lecture went over real well, apparently. Ryan?
I guess my understanding of it is that it tells us how precise our equipment was to make the measurements.
Okay. It is a much easier way to track the precision through calculations as well, not just starting with the measurement, but through calculations, than to do the accurate calculations for tracking the precision through calculations. So when we take measurements, like in lab, we always do show our plus or minus values. But then after that, we only track our precision by using the significant figures. You know, you can calculate with your calculator numbers out to like 15 total digits. But you might only have 4 of those that mean anything, and the rest of them are random numbers. And it's rather ridiculous to write down those random numbers. And if you write them down, somebody's going to assume, well, they must have been significant. Why would he spend all the time writing down all these numbers if they didn't have any meaning? So we use significant digits, the rules of significant digits, so we only write down the numbers that are meaningful in our calculations. Now, to make sure we're clear, when do you apply your rules of significant digits or significant figures? After you finish the entire problem when you put in your answer. Don't apply the rules early, because then you're going to be throwing away information and making your answer less precise. So you wait until you're done. So, a couple questions about precision here. Look at this. I'm halfway through my slides. I'm going to go a lot slower when we get to the next ones. Okay, so how many significant figures are in the quotient of 539.35 divided by 600 equals, and I wrote out the number to a very random number of digits. Well, they're both numbers. It doesn't have to be a measurement. We have those numbers which have significant figures, and when you do the division, you have significant figures in your answer.
Sure. I guess I was just thinking if you divide a measurement by a scalar.
Oh, okay, I understand. You're asking, is that 600 a cardinal number? Exactly. For my purposes, it was not supposed to be a cardinal number. Okay, we have had, everybody answered. Let's see, by the way, Toussaint, Jerry, and James. You 3 people apparently don't have the right clicker addresses for. I see clicker addresses, and they're not the ones that I have assigned to you. So if we can check those sometime, I'd appreciate it. Otherwise, you don't get the full credit like you're supposed to at the end of the semester. Obviously, we got some time. Okay, we had 14 people that said 1 significant figure. We had 8 people that said 3 significant figures, and 1 person that said it's ambiguous. And that one lonely person is the correct one. Now, Ryan was asking a question that I hadn't thought of when I made this. If that 600 was a cardinal number, that is, if a cardinal number is infinite significant digits, it's exactly 600. Like I have my pizza and I'm dividing it 3 ways. It's exactly 3 people who are going to be eating. It's not 3 1/4 or anything like that. In that case, this would be infinite, and the answer would have turned out to be 5 if 600 was a cardinal number. 600 itself is ambiguous. It could be 1 significant digit, 2 significant digits, or 3 significant digits. You can do things to help yourself out, like putting a bar over one of the zeros to indicate this one's significant. But if you don't, you just don't know. If there had been a period here, that would have also told me that all 3 were significant. So it could be 1, could be 2, could be 3. So any of these answers could have possibly been correct. So the only ones that were definitely incorrect, 4 and 6, definitely incorrect. And G is the correct answer because we really don't have enough information to know if it's 1, 2, or 3 significant digits in the answer. Yes.
So if we get something like that on the exam where we're not told how many significant digits for that, what do you want us to do?
If the problem is specifically about significant digits, if it asks you how many significant digits, then write down your assumption. Right? Because I grade on your process and explanation. So if you write down, I am assuming that this is 3 since it's ambiguous, I'm like, oh, she totally got that.
Okay. So
Right? Regardless of what I was looking for or expecting.
Okay, so if we just write like we're assuming that this is only significant to 1, or we're assuming this is only significant to 3.
Yeah.
Okay.
Now, if it's not a problem that is specifically about significant digits, go ahead and assume that the trailing zeros were significant. That way you don't end up with an answer that is wrong per se. You just end up with rounding differently. Yeah.
I was just, in general chemistry, typically his convention was if there's a decimal, then they're all significant. If there's no decimal, then the zeros are not. Is that not a science?
Well, if there's a decimal, then they are.
Definitely. But
If there's not, it's ambiguous. You don't know. Okay, that one, the one people usually do better on. This one, the one they usually do worse on. Now I changed the number from 600 to 601 so that this number now is not ambiguous. And I asked what's the significant figures for the sum of these two numbers. Okay, we have, and you can see that, yes, this is much harder for people. There is only one correct answer here. There's no ambiguity. But we have a range of answers given. Fortunately, the one with the plurality is correct. But let's go over how we get that so people know. Now, on the test, you are going to have one problem that asks you about significant figures. And when you have that problem, you'll need to have your explanation. And so for this, I would write, when adding or subtracting, the greatest of the least significant digits is the least significant digit in the answer. Now, those are all the exact words. You could abbreviate like LSD for least significant digit. It makes a lot more sense when you actually show the addition. So I show the addition with vertical addition. So I show it like this, and then I identify which one was the least significant digit in each number. Least significant digit is the smallest value that was significant. So in this one, that was the least significant. In this one, that was the least significant. And then I simply ask myself, which one was in a larger position? The units is definitely larger than the 100ths. And so I just draw this little dashed line to the right of the greatest of my least significant digits, and every digit that's on this side of that is significant. Yes?
Would you keep the decimal?
Yes, I would actually write something either 1140 period or 1140 with a bar over it. Bar over it means repeating if it's on the right side of the decimal. If it's on the left side, it means this one here is significant. So these are two ways of writing 4 digits as significant. And if you're curious, yeah.
Sorry, could you use the bar if you wrote out more, like if you had something that was like 0.47916 or whatever, if you just had a bar over the 4?
I think you could, but I'm not sure why you would. Because what you said is all these other digits are meaningless, but here they are.
Just in my experience for continuing calculations.
Yeah,
To retain the,
I do write down numbers for continuing calculations.
the bar helps me keep
Yeah.
track of the fourth digit.
Alexis.
Okay, so pulling from the last slide, if we didn't put a decimal, it would be ambiguous.
This here, 600 without the decimal was ambiguous. If it had a dot there, then this would have been the answer.
So, but the next slide, if we had
Well, I put extra digits on here to make sure that nobody thought that I was writing the limit. But I'm not sure what you mean. You mean it like if I had written it like this?
Yeah.
Yes, that would then be ambiguous the way I wrote it. I know that it has 4, but I wrote it in a manner that doesn't communicate that it has 4. Right. The way I write it doesn't change how many significant figures it has, assuming I wrote it correctly, but it also may not communicate. All right, I think we only have one clicker question on the rest of the way out. We're going to be doing more with problem things instead of just asking simple questions. So, by the way, on that, I wanted to show on the test, if you just circled the answer for 4, how many points would you have gotten for that problem? 1. I want to make sure everyone is 100% clear on that. I don't want people to lose points because they didn't pay attention. Where did the other 9 points come from? All the other stuff. Me writing down how I determine the number of significant digits in an addition problem and then showing the calculation. And in this case, there is no figure. I mean, showing the adding is part of the calculation, not a figure unto itself. And so more points get added into the concept part. So there would be basically 2 points for your work, 1 point for the answer, and 7 points for saying the greatest of the least significant digits is the least significant digit of the answer. Yeah?
Will you tell us when we don't need to include, like, let's say...
I will tell you when you don't need to include a figure.
Okay.
Otherwise, I will not tell you because you'll be looking at the problem and, sometimes problems are simple conceptual problems, but you don't want to tell a person, this problem is a simple conceptual problem, you should know it. You want them to read it and figure it out. And so you don't say, you don't need any equations or work on this one, because then that takes away the thinking from the student. Okay, chapter 2. We had kinematics. And we started off learning about vectors and scalars and coordinate systems. Now, why did we learn about vectors and scalars and coordinate systems here? Good question, because it was one-dimensional in chapter 2. One dimension means your coordinate system goes up and down, or left and right, only in one direction. But it was introduced here just to keep things simple. And so in one-dimensional motion, we generally just use positive numbers to indicate one direction, negative numbers for the other, because it's just one direction. Who cares how it's tilted? It's still just one direction. What's the difference in a scalar and a vector?
Scalar only has magnitude, vector has direction and magnitude.
Okay, scalars only have magnitude. Now, when we say they only have magnitude, that doesn't mean they don't have units. They still have units, because the units is part of the magnitude, right? 6 feet is different than 6 meters. The units was part of the magnitude there. But you have a direction if it's a vector. So I would have like 6 meters north. That's a vector. Whereas 6 meters by itself is a scalar. So vectors can be written as scalars. Scalars like, let's say, my mass. There's no direction for my mass. It's just a measurement of how much of me there is. So we can't put a direction on something that's intrinsically a scalar. But something that's intrinsically a vector, we can write it as a scalar. So we just need to be clear on the difference in a scalar and a vector. Let's look at some examples of vectors versus scalars. So let's see. I think that's about everything we've done. I put D here for distance. Actually, I'll change that to X because X is usually the symbol we use there. So, X, position. Is that intrinsically a scalar or a vector? Intrinsically a vector because you have direction to go with it. You can express it as just a distance without direction. So you can express it as a scalar, but it's intrinsically a vector. You have direction for it. How do we indicate when we write that it is a vector? An arrow over it. Okay, what about velocity? Vector. And I said velocity because if I'd said speed, Speed is the magnitude of the velocity and intrinsically a scalar because of that. What about mass? Scalar. Time? Acceleration? Vector. And force? Vector. Now force, we've talked about, it won't be on the test. The acceleration is an interesting example of a vector because acceleration is defined as the change in velocity divided by the change in time. If something is stationary, what's its velocity? 0. If its velocity is constant at 0, what's its acceleration? 0. Okay, I asked those questions just to make sure we have a baseline of where to think about these things. Now, if I have something that's velocity is increasing and it starts like at time 0 it's 0 and at time 2 seconds it's 4 meters per second east, what's the acceleration? I think I went 2 seconds.
Oh, sorry, 2 seconds.
So it'd be, I think, didn't I say 2 seconds later? Or did I say 1 second? Okay, so yeah. So it'd be 4 meters per second east minus 0, because that was my starting, divided by 2, and I'd have 2 meters per second squared east divided by 2 seconds. Now what if I started going 4 meters per second east, and 2 seconds later I'm going 4 meters per second north? I just realized I actually was using the right directions. So I paused there for a second. I was shocked. What's my acceleration then? How do you calculate it? Okay. Trying to look at people who haven't answered something today. Ann. Do you go as Ann or Annie? Ann. Okay. And how do I plug in my numbers to that equation? Divide by 2 seconds. I assume that for you. That's correct. How do I subtract east from north? Say louder.
So you can't, they're different, like they're parallel, so perpendicular to each other, so they're different.
Well, as far as direction, we can actually calculate that because I can take a graph and I can say, okay, here's my V initial, here's my V final.
We get the resultant vector, but you can't just be like it's north minus east. You can't just be like
Right.
north.
I'm going to get an angle that's not just north or east. And so if I'm subtracting these, I'm going to take V final, my V final vector, and I'm going to subtract V initial. When we subtract a vector, what do we do? Yes, we add the negative of it. So if V0 goes that direction, then minus V0 goes that direction. Remember, you add vectors head to tail, so I started at my origin. I didn't write origin, I just started. I draw my first vector, and at the head of the first vector, I put the tail of the second vector. And so this here is minus V0. And then how do I get the resultant? Straight line starting where I started, ending where I ended. And that was almost there. And so there is my delta V vector. Now, if I'm going to do this graphically, That's if I'm going to actually calculate my answer graphically. When I'm doing my work, like on the test, I would always sketch it out like this. Well, not always, but for the beginning level, I would sketch it out like this just so I can see what's going on. But then I would do analytical methods to get my answer unless I'm told to do it graphically. Now, you may or may not have a problem that has you do it graphically. You definitely should be prepared because it certainly could be there. So if I'm going to do it graphically, I have to have a scale. I actually have a slide coming up that has these, but actually no, it was on this one. Nope, it's in the next chapter's one. Let's not worry about where it is. I have to have a scale, so I say like 1 centimeter is equal to 1 meter per second. And then I measure out a length of 4 centimeters to go with 4 meters per second. Carefully lay them out perpendicular. And then I take my ruler and I measure the length of that. And I see that that's 5.6. Now, in terms of directions, I'll measure an angle. Let's say I measure this angle. And I think we all probably know enough to say that that angle was 45 degrees. And so I'm going to get my acceleration is equal to 5.6 meters per second at 45 degrees, going what direction from what reference point? That's correct, going west of north. I'm not done yet. Divided by 2 seconds. Right? And so then I get my answer. That would be, half of 5 is 2.5. 2.8 meters per second squared at 45 degrees west of north. So that's how I would get it graphically. I would measure this angle and I would measure the length. Now analytically, I did this in my head obviously using the analytical method. How do we do it analytically? Okay? We need our trigonometric functions and we need Pythagorean theorem. So in this case I had a 4 and a 4, and that's a right angle because our coordinate system has to have mutually perpendicular directions. So I used the Pythagorean theorem. Square root of 4 squared plus 4 squared equals 5.6. That's how I got the 5.6 meters per second for the change. And then for the angle, opposite side was 4, adjacent side was 4. So if I call this theta, I'm sorry, my colors are now all out of whack with anything educational, but I can change them. So now magenta is the analytical method. So I used Pythagorean theorem to find the magnitude of the change in velocity. And then I used, and actually I think I'm going to write this out more clearly. I have tangent of theta is equal to the opposite side, 4 meters per second, divided by the adjacent side, which was also 4 meters per second. How do I find theta if I know tangent theta is 1? I take arc tangent, which is the inverse tangent. If I do inverse tangent of tangent, it's an inverse function, which by definition of inverse function means it's going to give you back the argument. Theta here being the argument of tangent. So if I do arc tangent on tangent theta, remember arc tangent and inverse tangent are the same thing, then this side will become theta. And the other side will become arc tangent of, and I just put 1 because 4 over 4 is 1. And so then I punch in my calculator arc tangent of 1, and it pops out 45 degrees. So we have the analytical method and the graphical method for adding the vectors. Yeah.
Why did you switch the direction again?
Because I was subtracting. Right, the equation for acceleration was change in velocity divided by change in time.
Oh, okay.
So that's velocity final minus velocity initial. And to subtract it, you add the negative of the vector. It's an important concept. Okay, additional words. We've talked about displacement, time, velocity, speed, and acceleration, so I guess I can stop there. The kinematic equations. You will be given the Pythagorean theorem. You'll be given the definitions of sine, cosine, and tangent for a right triangle. I'll go ahead and put on the law of sines and law of cosines because, well, we found that especially that law of sines can be useful. And then you'll have the 5 equations that our textbook lists as the kinematic equations. I'm not sure if that included the definition of acceleration, the definition of velocity. I'll put those in as separate equations, I guess. That's pretty much all you have for equations up through chapter 3. You also have, of course, G is 9.80 meters per second squared constant. Yeah, you don't have to memorize that. Speed of light will be there, although I'm doubting you'll need it. Cassie?
Yeah, will all of this be up online today?
Yeah.
Okay, just double check.
You have a question, Ryan? No. Okay. Okay, so we have those kinematic equations. Now, with those kinematic equations, the textbook listed 5. I usually only list 3. The 3 I list are now, this last one is written like 4 different ways, 3 different ways, depending on if you're looking for position, acceleration, or velocity. I happen to write it in this case in the way you'd write if you're looking for position. I trust everybody has the mathematical skill to solve this for any one of the variables. These are the 3 kinematic equations that I consider the kinematic equations. The other 2 the textbook gave were the definition of average. That is velocity average. If acceleration is constant, is initial velocity plus final velocity divided by 2. And that position is equal to initial position plus average velocity times time. Those were the other 2, that the textbook gave. I don't consider those as much kinematic equations because they have the average in there. All of these equations apply in one specific case. This one specific case that for general physics is all we work with in kinematics. What's that one specific case for these to be correct? That's right. If acceleration is constant. If acceleration is not constant, these equations aren't correct, okay? And so your problems will always be constant acceleration. Now, you might have constant acceleration from time 1 until time 2, and then from time 2 to time 3, you have a different constant acceleration, but you won't have a changing acceleration. It will be constant segments. That's because you have to use calculus. So my 9 people in the calculus-based class, which is, I think, the biggest calculus-based class I've ever had, you may have a problem where acceleration is not constant, and you have to work out your own kinematic equations for the situation of whatever acceleration I might give you. Okay, so we have those kinematic equations, problem-solving basics. Here I put the step of how to solve a physics problem. Wait, nope, this first, the coordinate system question, this is the last clicker question, and then how to solve physics problems. For a 2-dimensional coordinate system, what spatial relationship must x and y directions have? And of course, this one question you've already seen. Okay, we got 23 answers. 22 said they must be perpendicular to each other, and one person, I'm going to assume, is mocking me. The correct answer is that they have to be perpendicular to each other. If they're perpendicular to each other, that means that we can use the definitions of sine, cosine, and tangent that you're used to. Things like sine is opposite over hypotenuse. That's not true if it's not a right triangle. But if we have our components perpendicular to each other, our components will form a right triangle. And we can use that. Okay, now let's go to looking at a problem. How to solve a problem. First, examine the situation, determine what physical principles are involved. For our test tomorrow, what physical principles do we have? Yeah, the kinematic equations, the end. You might have questions that are not physical principles like significant digits and stuff like that. I mean, then you're going to put down that's what's involved, but it's not really a physical principle. It's just a bean counting principle. So you're going to have kinematic equations. It's not very hard to determine what your principle is involved if you have an actual problem. On the other hand, we've started chapter 4, dynamics, and in dynamics, we then have, ooh, this is a Newton's second law problem, or ooh, Newton's third law. And so we're going to have a total of 3 things, and we can start combining them. So for instance, Newton's second law allows us to take forces and find the acceleration on an object that's going to result from those forces. But then once you have the acceleration, then you have a kinematics problem. So as we go through chapters 4 and 5, we have more concepts, and we might have concepts tied together. And so the physics is in understanding how to apply those concepts and tie them together. Okay, step 2, make a list of what is given or can be inferred. Things like the acceleration of gravity, something we will infer. It doesn't have to say you throw the ball and what happens and the person says, oh, they didn't say there was an acceleration. I think it just keeps going forever without changing velocity. Right, you infer, yes, there's acceleration of gravity, because it didn't say that we were on Mars or the moon. It just said you throw a ball, and we know that you're on Earth. Identify exactly what needs to be determined in the problem. Right, I, as a teacher, have taught this class for, this is the 21st year. And so these problems really become old to me. And so a student comes in and asks a question about a problem, and I will just read like the first sentence and say, oh yeah, I know where this is going. And I'll solve for an answer, and then they'll say, well, yeah, that was in the second sentence. It asked about something completely different. And then I feel like an idiot because I spent all this time calculating something that was given in the problem. You need to make sure you read the problem carefully and identify what you're looking for before you start looking for it. Okay, step 3. Step 4. Find your equation or set of equations. If we look at this in terms of units or of points, this here is 3 points right there, right? On the test. This here is going to be 2 points. Find an equation or set of equations that can help you solve the problem. 5, substitute the knowns along with their units into appropriate equation and obtain numerical solutions complete with units. That's another 2. And then the answer, check your answer to make sure it's reasonable and makes sense. That's 1. Where's the final 2 points that aren't shown here? The figure.
How detailed do the figures have to be for the test?
That's a good question. The figure needs to illustrate what's going on in the problem. So it needs to be not factually incorrect or not missing an important piece. But it doesn't have to be, Hannah's a wonderful artist I have seen already. You don't have to draw figures as good as Hannah's figures. I am a horrible artist. You can get away with figures as bad as mine.
So like stick figures or like just lines?
Yeah. I usually use stick figures. I might use a box for a person if I am pushed. A box is a fine representation of a person.
Okay.
A ball, not so much, because a ball would roll down an incline, a box would slide down. A person's more likely to slide them, I suppose. Depends on the situation, I guess. If Jack and Jill climb up the hill, well, then the ball might be the better. Okay, so we're going to use these. We're going to do them on the I say we're going to. You're going to. Use these on the test. Make sure that you follow these guidelines. Why? And there's the obvious question. I knew that answer as soon as I read the question. You made me draw a figure, write down an explanation about what's going on. Yeah, because I want to make sure that you have been able to show that you know how to do it, and when you get a problem that you couldn't answer right off the bat without doing any work, that you can still work your way through, that you have a way of getting through a problem. Reagan?
Are those guidelines going to be on the test somewhere so I can see and just double check?
You will have the points.
Okay.
You won't have these guidelines here, but you'll have the points, what they're broken down on. So it'll just say figure 2, concept 3, and like that. Okay, so a practice problem. By the way, I took this from this website. This isn't the picture from the website because I didn't want to give away the picture before we start. But this is actually, it's a nice website that just leads you through the steps for how to solve the problem. And since this is 2, I assume that there's a 1 and maybe even a 3. So we have a problem. You want to throw a ball straight up in the air so that it reaches a height of 3.3 meters. Somewhere up there. And your hand is 1.2 meters when it leaves the ground, so it's leaving your hand right about here. And how fast do you need to throw it is the first question. How long does it take the ball to hit the ground is the second one. Now I use red here to highlight what it's asking. That won't be on the test either, right? You'll have to identify what it's asking. So what should I do right off the bat? Draw a picture. Now this picture here is not a complete picture. I did that intentionally. If you go to that website, you'll see they have a nice little stick figure, very simplified picture to illustrate what's going on. And it looks an awful lot like this. Y1. They use Y1 there, so that's why I'm using Y1 in case you're wondering why I used 1 instead of 0. It starts with a height of 1.2 meters. Up here, Y2 is 3.3 meters, and down here, Y3 is 0 meters. That was all information I knew. Got a question?
Why is it Y? Shouldn't it be X?
I was actually going to ask, why am I using Y? Why is it Y rather than X? Traditions. They're doing Fiddler on the Roof over there this year. My boy's going to be Moto. I'm very proud. And that we have the song, Traditions. That's why. Okay, realistically, why do we have that tradition? If we have 1 dimension, we usually use X. If we have 2 dimensions, we use X for horizontal and Y for vertical. If we have 3 dimensions, we use X for horizontal, 1 direction, Y for horizontal, another direction, and Z for vertical. You might immediately say, I see the flaw. It should be Z for vertical because we're in 3 dimensions. You could use X, Y, or Z, and it doesn't matter. It's just, if we're doing a 2-dimensional problem, we use Y for vertical and X for horizontal. And even though this is 1-dimensional, we fall into thinking of it as a 2-dimensional problem. Did you have a question, Ann? Okay. So that was a good question. Okay, what other information do I have or am I looking for? Okay, I have the acceleration of gravity. I have not been told the acceleration of gravity. I'm inferring that. Now, my picture has a redundancy in direction. I can solve that by going like this, but, right, because I put A is equal to minus G, and then I had an arrow down. And technically that says this arrow has a length of minus G, which would mean it would be up. I just haven't figured out a way to best deal with that. But when I'm doing calculations, I need to have A is minus G. I consider up positive, so I'm going to write over here, there's my positive Y direction, and that's why my A is negative, because it's down. Okay, so that was something that was inferred, not given. What else? There's another inferred value.
Velocity at the top will be 0.
The velocity at the top has to be 0. Now let me ask a very important, I ran out of time and I didn't get 3 dimensions. I didn't finish this question. A very important question here, though, to make sure people are on top of this, because I saw a lot of people that still seem to have a problem. What is the direction of the velocity as the ball is going up? No, the direction of the velocity. Not what's happening to it, but what direction. That's right, Diksha. You have the velocity is going up on the way up. What's the velocity on the way down? Down. Otherwise, we wouldn't say on the way down. What's the acceleration on the way up? Down, okay? What about on the way down? The acceleration is down. What about at the very top? It's still down. A lot of people get acceleration and velocity confused, and they think they have to have the same direction and things like that. They don't have to have the same direction. They don't have to have the same magnitude because they certainly don't have the same units. The acceleration is the rate at which velocity is changing. I'm sorry I wasn't able to finish. The next step here would have been to decide what kinematic equation I could use, which is the v final squared minus v initial squared is equal to 2a x final minus x initial, and solve it. The only thing that's added in Chapter 3 that I didn't go over is independence of motion. Independence of motion, horizontal motion is completely independent of vertical motion. And so you basically, when you have two-dimensional problem, you just have 2 problems. One's the horizontal problem, one's the vertical problem. Vertical problem you do just like this. Horizontal problem, the acceleration 0. Okay, I'll see y'all tomorrow at 2. Obviously, there's no pre-lab quiz since we're not doing a lab activity.